lecture number 3. And before we go ahead with the lecture, let me make one announcement. Namely that please ignore references to early chapters in the lecture notes that I'm going to send you. And you should start with, we started with chapter 7 of my lecture notes. So that references to chapters 1, 2, 3, 4, 5, 6 can be ignored. And the thing is that I taught 311 before, and I wrote the lecture notes for both 311 and 412. And since I'm teaching only the second half of this EMM course, so we will cover chapter 7 and onwards. So forget about the references to early chapters. Whatever I mentioned about the early chapters, you can figure it out yourself or by looking at the book by Griffiths. Okay? All right. So last time, you remember, we quote unquote derived Maxwell's equations in terms of the divergence and curl of the electric field E and the magnetic field B. Given in terms of the sources. And one thing that was missing in this equation was this term, and it was put in by Maxwell, taking into account the conservation of charge, namely the divergence J is in general not zero, but it's equal to minus the rate change of the charge density rho. All right? To go along with this set of equations, you also should recall that we have to use Lorentz force law. Namely, the force law says that a force acting on a charge Q by the field E and B are given in this form. And since Maxwell made use of charge conservation to put in this term, so obviously Maxwell equations already contains this requirement of conservation of charge. Of course, this is easy to do. Namely, take the divergence of this, the right hand side, the left hand side 0, since divergence is equal to 0, then divergence J is equal plus this term, then del by delta of divergence E. Divergence E is nothing but up to this factor 1 is rho. So that you have divergence E, you have del rho by delta here, and combine it for the conservation of charge equation. So that is included. All right? And last time, you remember, at the end of the last lecture, we said that let's in fact talk about the case that the sources rho and J being 0. In that case, the pair of equations, the four equations in Maxwell's equations, they're in this form. And we noticed that the equations look very similar for E and B. In fact, the Maxwell's equations are invariant under this so-called duality transformation, which says that under this transformation, E goes into B by multiplying this factor, and B goes into minus E times this factor. Minus sign is necessitated because of the fact that there's a minus sign on this Maxwell's equation, where it's plus C. And this factor got to be there because, as you recall, E and B have different dimensions. E has a dimension of speed times speed, so that you need something having a dimension of speed times speed. That's something is in fact C. And we would mention again that in fact 1 over square root of epsilon naught mu naught is nothing but the speed of light in vacuum. So that E goes into B times something having a dimension of speed, which is a C. And inversely, this one, B goes into, aside from minus sign, E divided by C. And so that is divided by, so it's 1 by So that the four equations are invariant, meaning that this equation goes in this equation goes in equation, and vice versa under this transformation. And it is nice also to have some kind of symmetry in your theory, and this is a nice symmetry. But unfortunately, this symmetry is gone once you put in the sources in Maxwell's equation. It's rho is J in Maxwell's equations. And to recover, Lorentz transformation symmetry, one has to put in the analog, the magnetic analogs of the electric touch density and charge and the current density. And let me do that. And I anticipate that one over epsilon naught will be replaced by mu naught. And let me put in the magnetic charge density. And let me, in fact, put in subscript E here for this electric charge density, and put a subscript M here to denote magnetic charge density. And similarly, here we have distance to one side, we'll put into minus mu naught times the magnetic current density, which we will call denoted by J sub M, and attach E here to this electric current. Now, this reminds me that in the lecture notes, I did not put in subscripts E and M. Instead, I caught in the lecture notes. Instead of rho sub M, the magnetic charge density, I use the notation eta. And instead of J sub M, the magnetic current density, I use K vector. And I use K because once J after J is K, so that's why I use K. That's natural. But on second thought, just now, very good notation K, since K in for us also stands for the surface current density. But anyway, if you see, when you see eta in my lecture notes, mentally, just replace it by rho sub M. And K in this context, when you know that it is talking, we are talking about the magnetic counterpart of the current density, replace it by J sub M. All right, but for the lectures, let me use rho sub E, rho sub M, J sub M, J sub E to stand for the current and the charge density. All right. All right, and to have the symmetry on the duality transformation, which transform this equation to this equation and vice versa, this equation to this equation and vice versa. Of course, we have the need to have transformation on the sources, and it is relatively simple to figure out what that should be, and you can check that the following is true. Namely, the rho E goes into square root of epsilon naught mu naught rho M. And the JE goes into this vector times J sub M. And at the same time, rho sub M and J sub M goes into rho sub E and J sub E. By there's a minus sign, and the reciprocal of this 1 over square root of epsilon naught mu naught. So the direct transformation is now generalized to this four transformations. E equals to B, B equals to minus E, rho E equals to the rho M equals to rho E with its respective factors. Let's check. Okay. Oh, okay. Now, in fact, I should be using the, okay, this is the case only when external sources are not there. So let me erase this. So I'm saying that the product transformation, oh, it's not big enough. Under the product transformation, this equation will solve rho of E and goes into this equation, rho of M, and this goes into this. And let's check. And I do not have that space big enough. Okay. Oh, before I do that, let me, since I've written down the Lorentz force law here already, so that this Lorentz force law should be generalized to the following, namely that force acting on a particle with charge, electric charge Q sub E is multiplied by this. And then, of course, on top of that, you should have the counterpart of this equation, taking into account the direct transformation. QE goes into QM, E goes into B. Okay. B goes into essentially minus E, so minus V plus E. And to have the dimension correct, you need to have a factor of epsilon naught mu naught, which has dimension 1 over speed squared. Cancel with this one factor of speed, then we have here. This we have the dimension 1 over speed. Yes, okay. B has dimension of E divided by speed. You can check that. The Lorentz force law has to be generalized to this. Put in this term also. So that under the quadratic transformation given here, this goes into that and vice versa. All right, so let's check one equation. Okay. Name it, this one. Let me take this equation. Okay. Under the direct transformation, I'm going to show you that this equation goes into this equation. And you can check that this goes into that. So let me, okay. Under the direct transformation, the left-hand side goes into curl of E goes to B with factor of square of epsilon naught. This left-hand side goes into that. And the direct transformation is equal to minus mu naught. Jm goes into this. Minus 1 over square of epsilon naught mu naught Je. This goes into that. And then B minus del B by del T minus del B by del T. B goes into minus E, so minus plus E, and there's also a factor of, okay, this square of epsilon naught mu naught. Let's check to see if this equation obtained from this equation under the direct transformation is in fact the last equation of the Maxwell's equation, the so-called Ampere-Maxwell law. Let's see. So to do that, notice that this minus is cancelled. So let me erase the 2 minus sign and forget about the bracket. Okay. Let's multiply both sides by square of epsilon naught mu naught. And this multiplied by this factor. Okay, there's one factor there already. So that would be the square of this. So this is not square. So under direct transformation. The furthest law goes into this, which you can see is nothing but the ampere Maxwell left hand side curve B, and mu naught JE plus epsilon naught mu naught del E by del T. So it works. All right. And let me see. I should also mention one more thing about the Deutsch transformation, namely that since we have charge density transformation, of course, QE upon charge with electrical charge QE would go into this thing factor, square epsilon naught mu naught Q sub M. And this Dm, rho M, would contain this transformation Qm goes into minus 1 over square root of epsilon naught mu naught QE. Okay. And now let's take a look at this equation. Just as in this equation, from using this first the Gauss law, you can write out the electric field E due to a point charge Q. Let's say that at the origin, Q at the origin, that would give rise to electric field E at the location R hat given by 1 over 4 pi epsilon naught QE over R squared times direction pointed towards E is R hat. Oh, times the unit vector pointed from the source QE towards the location where you want to measure the electric field. Then analogously, by using this equation now, we have the point charge, point magnetic charge, Q sub M, at the origin of the coordinate system, then it will give rise to a magnetic field E at the location R given by zero expression C. Instead of 1 over epsilon naught, now you have mu naught over 4 pi. QM. Okay, it's R hat over R squared. R hat over R squared. It's easy to rewrite this as multiply. If I multiply both upstairs and downstairs by factor of R, this will be nothing but R vector divided by R cubed. So let me use this one. R vector over R cubed. This is the counterpart of the Coulomb's law. Okay, and now, let us see. So we have introduced the magnetic analogs of the electric charges and currents. And you may ask, that's nice to have that kind of symmetry, but what does it really do? Okay. And before I tell you what the introduction of magnetic analogs of those electric charges do, let me mention one thing. A story, true story, because it affected me and indirectly the department. Namely that, so if the magnetic analogs of rho M and Jm exist, this means that there could be magnetic charges or magnetic monopoles, some people call. And it turns out that in grand unified theories, unified electromagnetic interactions with weak interactions as well as strong interactions, it turns out that in those grand unified theories, okay, and the study of which, okay, was in vogue, okay, in the late 1970s and early 80s. Okay. And it turns out that, okay, granular theories, okay, predicts the existence of magnetic monopoles. Not only that, one can figure out that those magnetic monopoles are very massive. So massive that, okay, you do not have to take too many those magnetic monopoles to overwhelm the cosmic expansions, so that in fact if the granular theories are correct in the prediction of the existence of those massive monopoles, okay, then the universe would have, in the early universe, would have collapsed due to those massive attraction, due to those massive magnetic monopoles. But of course, the universe did not collapse, otherwise we would not be here. So there must be a way to get rid of those monopoles if the granular theory is correct. And it occurred to one postdoc at Cornell at that time, the idea. Okay, his name is Alan Guth. Alan was a graduate student at MIT when I was a graduate student at Harvard, although we did not know each other at the time. Alan was a postdoc at Cornell at that time, and he thought about this problem of the monopoles and the collapsing of the universe. And the question is how to dilute those monopoles so that the universe could avoid the collapse. Well, to dilute the density of monopoles, well, he thought, well, what if the universe underwent a rapid acceleration, expansion, which he called inflation, so that the volume offset in a short time started with a very small volume, goes into a relatively large volume, diluting the density or the number of monopoles, so that the densities would be low enough to avoid the collapse of the universe due to those massive monopoles. And that theory he called inflationary universe. Theory or model. And that was a very extremely nice idea. Well, now, this is a sad story. I came to UNC in 1978, and a year later, I was the first particle physicist in this department. And shortly after I came here, I asked the department to give us one more position in particle theory. And graciously, the department obliged, and they allowed me to find someone in particle theory to join the department. At that time, I was working with my former high school classmate at Cornell. And at that time, I went up to Cornell and I asked my former classmate, is there someone real good who's looking for a job, in particle theory? And he said, yes, a fellow postdoc, my name is in fact looking for a job, and he's good. I said, okay, I'll invite him to join me. So the next morning, I happened to run into Alan in the cafeteria, and I said, Alan, would you like to join me at Chapel Hill? To my great shock and surprise, in just a few seconds, he said, no thanks. I was extremely disappointed. And I could not understand why he would turn down. Because at that time, jobs were very, very scarce. And he was looking for a job. Only later did Alan and I find out our misunderstanding. Alan thought that I was offering him a postdoc job, not a faculty position. And I thought that my former high school classmate must have told Alan already that I was looking for someone to join me as a faculty member. So he misunderstood, and I didn't realize that he misunderstood what my offer was. So of course, not surprisingly, he didn't come. So that was a great loss to me and to the department. Because shortly after that conversation, Alan started working on inflationary universe. If he had come to Chapel Hill, he might have developed his theory of inflationary universe here in Chapel Hill. Instead, we got no credit. My fault. Well, enough for story. Anyway, so that there was a problem for the for cosmology if those massive magnetic monopoles exist. On the other hand, it turns out that if even a single monopole exists, it would do great wonders to the theory, to physics, theoretic physics. I'll show you why. And what I'm going to tell you was originally due to Paul Dirac of the Dirac data function frame. So Dirac said, let's assume that in fact there's a magnetic monopole. Let's put it at the origin of the coordinate system. Then of course it will produce this magnetic field B. And let's say that there is a particle with charge with mass m and electrical charge with charge q sub e orbiting around this magnetic monopole. Let's examine the equations motion for this point charge due to moving in this field generated by this magnetic monopoles. All right, and I think I can erase this. Okay, let me write down, use Newton's law. What is mass times acceleration? Mass times acceleration, so d dv by dt. V stands for the velocity of this electrically charged point particle. That's equal to force acting on it. Well, force, you remember, is the following. This particle has charge QE. Now it is acted on by the magnetic field B. Given this one. This. So the QE V times that. Just V cos R divided by RQ. And then I have this mu naught, the QM, QE, and then I have this factor of mu naught over 4 pi. That's the equation motion for this electrically charged point particle with mass m moving around a magnetic monopole. Okay? Next, let's take the moment of both sides of the equation. By that, let me multiply r from the left on both sides of the equation. So that I have r cos dmv by dt on the left, and on the right side I have mu naught over 4 pi QEQM, r cos v cos r over r cube. on left side. Okay, d derivative x on v to give us acceleration. Does not act on r. But let me put this r to the right side of d by dt. So they act on it anyway. So let me put this in. So I have d by dt, r plus l v. You said, well, you have done too much derivative. Now, d by dt x not only on v, but also on r. And you should take out this term when d by dt takes x on r. But it's okay, it's zero. Why? Because when d by dt is on r, it gives v. V equals v is zero. So I'm adding something which is zero. So that's fine. So that the left-hand side is a total derivative. And what is the right-hand side? The right-hand side is this. Let me, in fact, write this down. So this is a true cross product. So there will be two terms. One in direction of v, multiplied by r dot r, so it's r squared. The minus another term in direction of r, multiplied by r dot v, divided by r cubed. So there are two terms. One is, first term is v divided by r. The next one is minus, v dot r over r cubed. Here's the left-hand side is a total type derivative. We wonder if the right-hand side is also total type derivative. So, could this be equal to d by dt of something? If it was so, it would be nice. Then both sides involve a total derivative with respect to time. And the answer turns out to be yes. Let me show you. This quantity has a dimension of v over r. V is distance due time. So this has a dimension of 1 over time. Well, this dt here has dimension of 1 over time. So the whatever is inside square bracket, if this can be written in this form, got to be a vector, and got to be, in fact, dimensionless. Well, that vector has better be r. So this r. But it has to be dimensionless. That's easy. Divided by its magnitude. That will be dimensionless. Let's check to see if that's correct. It turns out to be correct. There are two terms. One is dr by dt divided by r, so it's 1 over r. dr by dt is a v. Then you have plus. Then you have r outside. Then you have d by dt and then 1 over r, which is minus 1 over r squared dr by dt. This term is this term. It's good. What about, is this term equal to that term? That's the question. And to do that, we have to know what's dr by dt. Notice that it's d magnitude of r by dt, not d of vector r. If it's d vector r by dt, of course, that would be velocity. But it's not. So, if you are sleepy at night, you look at this one, and you say, oh, this is the speed v. No, wrong, not that simple. R is a vector. And to figure out what is d magnitude of r or dt, you have to do the following. Namely that we know that r dot r is r squared. So that if I take the time derivative for both sides, this side there are two factors for r, so that it will be referred with 2r dot dr vector by dt now is v. And on the left right side is 2r dr by dt. So that dr by dt is, this is not v, but, it's small, but, r dot v over r. R dot v over r. Which, lo and behold, is, thus indeed my sign, in the denominator of r squared r is r cubed. There's r vector, then I have, the last thing is r dot v, correct? Yes. So that, in fact, this is a total derivative. So that this is this factor times d by dt greater than r over r. Let's put these two terms together. Put this to the left hand side. Then I have d by dt of m. So it's r plus mv, which has the physical meaning of orbital angular momentum. Yeah. And then there is this term also goes to the minus sign. Mu naught for q e q n r over r. That is 0. So that this term also has the meaning of some kind of angular momentum. So obviously, since you have d by dt action on the whole thing is 0, so this has the meaning of the total angular momentum. Let me call this J. And J, the total angular momentum, is a constant motion. d by dt action is 0. So J is equal to this one. But we know from a study of quantum mechanics that angular momentum is quantized. All the components of angular momentum takes on multiples or integers or half integers of Planck's constant. So that let me take a look at this at the component of J along the direction of motion. So that it has, aside from the sign minus, so it's mu naught over 4 pi q e q m has to take on factors of m. Let me call this n, where n is integers or half integers. So that the product of QE and QM is not arbitrary, but it's restricted to be such that up to this factor, the product takes on multiples, integers or half integers times Planck's constant. This is the quantization of charge. Namely that if there exists one magnetic monopole in the whole universe, so this is of certain value, then all the electrical charge particles in the universe go to obey this quantization rule. So that maybe this charge, point charge, is an electron, or it could be a proton. They all got to obey this quantization rule. And this explains the observed charge quantization. For example, we know that the electron carries a charge minus the charge of a proton, exactly minus the charge of a proton. So that the charge of the electron is not minus 0.9999 times the charge of the proton, not minus 1.001 times the charge of the proton because of this condensation. And that is this charge condensation is a nice thing to have. It exists. If there exists a single monopole in the whole universe, that would explain why all the electrically charged particles carry those particular charges. All the electrical charges are quantized. And this condensation is known as the direct condensation, charge condensation. So far we've been talking about a particle carries either magnetic charge or electric charge particles. But what prevents the scenario that there are particles carrying both electrical charge as well, both electrical charge and magnetic charge? And Schwinger, in fact, considered that possibility. And he called particles carrying both electrical charge and magnetic charge diode. Okay, so much so that indeed, it appears that we do not need magnetic analogs of our electrical charge particles, and no analog to the electric current density. But if a single monopole exists, we have nice thing for theoretical physics. So that I still wonder quite often whether in fact magnetic monopoles do exist in the universe. Not a lot, but just as I said, just a single one would do. Okay. Now we have spent quite a bit of time on introducing the magnetic analogs. JM and OM. And for the remaining of this lecture, I'm going to drop OM and JM, go back to the conventional Maxwell's equations. But I will come back to the generalized Maxwell's equations with OM, JM also on the right side of Maxwell's equations later on, when we talk about conservation laws. Well, there's no need, strictly speaking, to do that. But you see that if we do put in OM and JM in Maxwell's equations, the calculation is much easier. So for calculational purposes, in fact, it turns out that it's nice to have JM and OM in Maxwell's equations. We'll see. So remember that. But for this lecture, let me in fact now and go on to talk about another topic. Oh, by the way, if we kept the magnetic terms in the equation, you can show that there is the conservation of magnetic charge. My del rho is the divergence of JM. All right. So this now on this. By the way, Dirac, okay, you must have heard of the Dirac equations. Okay, Dirac was the one who predicted the existence of antiparticles, positrons and antiprotons, etc. And he was also a very interesting guy. Okay. He moved from England to Florida to live with one of his daughters in the later part of his life. In fact, he was present in the opening ceremony for the Moab Planetarium. He also is someone who seldom spoke. And in fact, there was a joke saying that people talk about the unit of talking. One Dirac stands for one sentence per day. All right. Let's now move on, and let me see, make sure that I'm Okay. Oh, okay. So now, let's talk about Maxwell's equations in the materials. Inside materials. And to start, let's consider a neutral atom. After all, macroscopic materials are made up of just collection of atoms. And inside the atom, there are a bunch of charges that we call Q sub I. I labels which charged particles being inside the neutral atom. So that we have a neutral atom. Sum of I, Qi is 0. Charges inside the atom moves around, but its center mass hardly moves. So it is convenient to use the center mass of this atom as the origin of the coordinate system. Let's do that. So we are interested in finding the force acting on this neutral atom due to an external electric field E and magnetic field B. And let's consider static fields, no time dependent. And these two fields vary very slowly as a function of position. So that we can write down the electric field E at the location where the ith charge is located inside the atom as the electric field E at the location of its center mass, which is the origin. Plus, the next term use Taylor expression, and this is slightly more complicated because this is a vector, but it's easy. Actually, it's easy. R dot gradient acting on E. And once you have done the derivative, this gradient operator, you evaluate the whole thing at 0. So then you pass that. And I will know high order terms. Similarly, go to the Taylor expression for the B field at the location of the ith particle. This will be the B field at the origin. B. Once the derivative is taken, you evaluate that at the center mass of the neutral particle. All right. So this is well, we have, of course, we use Lorentz force law to this system. Given by sum over I of Qi, E and Ri plus Vi cos B at the location of R. And now, okay, let's use of the Taylor expansion. So this will be equal to sum of I, Qi, this term. First term will be at E at the origin coordinate system, then plus sum of I, Qi of this Ri dot within acting on E, understood to be at the origin. Okay. And that, this term is more complicated. Plus sum of I, Qi, Bi cross E at the center mass, E, then plus. Okay. The most complicated term will be this one, the sum of I of Qi, Vi cross this, which is Ri dot gradient acting on B plus higher order terms, which we will not consider. And for this term, you notice that this is a cross product of Vi with B. But B, on the other hand, is acted on by this gradient operator. So I cannot put this somewhere else, because this acts on that. But as far as the vector product is concerned, it is Vi cross B. All right. This term is sum of I of Qi times this, which is a constant independent, okay, which particle which I talk about, so I can put it right here. But this is zero. This is a neutral vector. No. How about this one? Well, this one I can also put right in here. Sum of Qi Ri. What is that? That, of course, is nothing but electrodouble movement of the atom. So P, this stands for electric double movement. Sum over I, Qi, Ri. So this term is P dot gradient acting on E. Simple. What about this term? Well, this term instead of Ri is Vi. Okay. So this is, okay, I can put a bracket here. Okay. This is nothing but the time derivative of Qi Ri. So it's dP by dt. So that this term is, and I use red pen because it's important, was, namely this term is nothing but the rate change of a double moment, electric double moment, with respect to time, was E. And then there's this complicated term. Now, why have I singled out this term? Because this term involves d by dt. It's dynamics. And we are now talking about electrodynamics. So this is something new. This term will be absent in the static, in the study of electrostatics and magnetostatics. And this is new. The other terms are static terms. So then whatever the other terms are, it will not produce things that you have not learned in your study of the static cases, electrostatics and magnetostatics. And let me tell you, we can go ahead and calculate this term, etc. Okay, and it turns out it involves some algebra. Okay, involving vector analysis, sort of complicated. It takes time. Okay, and for those of you who are interested to know how this term, from this term we can recover some of the results that you have learned in your study of the study cases. I will just tell you the result. You can use this result to recover some of those old results. As along the way, of course, you can take this a check on the accuracy of your calculations. In the calculations, we'll be interested to just keep the lowest order terms. And all those order terms turns out to be involving the electric double moment expressed magnetic double moment. Those are the terms that we're interested in. We will not be interested in high order multiple terms. For example, this term, if it contains a little bit of the electric quadruple moment. That's high order term than the double moment. So we are not interested in that. And from the study of this, I'll show you that we will be able, if we include these terms, we will be able to deduce bound charge density as well as bound current density. And that is equal to, for the study case, you know that it's given by minus divergence of polarization. P is polarization, which is the electric double moment per unit volume. And the bound current density involves a term in the curve of the magnetic double moment. M. Or M is the magnetization. The magnetic double moment per unit volume. Magnetization. So if you include this term and work things out, you should be able to cover this result coming from the study of electrostatics. But now, I'm going to show you that in fact, there are new contributions to the bound current density coming from this term. Due to the fact that we are now talking about dynamics. Okay? So as I said, you're welcome to study my lecture notes and start with this and really reproduce these results. It turns out that this term is, let's say, turns out to add in another term. And this is the new term involving d by dt. All right, let me continue here. Should I? Okay, maybe let me keep this. And let me continue here. Okay, let's assume that we have found all the other terms. So the force acting on an atom is given by those terms, plus this term. This is a force acting on one atom. Of course, microscopic materials are made up of a bunch of atoms. So that to find the force acting on a piece of microscopic material, all you have to do is sum over all the forces. Sum over forces. And then also, let's go on to the continuum limit. So this will be given by as the volume integral of, okay, the density of those atoms, n, times this one atom. So this is one atom is dot 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 plus d by dt plus d. All right. So this is equal to n is the density of atoms, n times p. P is the double moment for one atom, so that you will have contributions coming from those dot terms, which we can include if we have worked out those calculations. But let's save time not to do that because we know the result already. Then plus, put this d by dt outside this. Oh, so this is equal to del by del t. D dt is for each particle, so that in fact I should replace this by del by del t. Del by del t acting on NP, as I said, is the polarization. Now let's compare this expression for the force acting on the piece of microscopic material to the form of the force given by the usual vector force law, except that we go on. This is for one particle. We go on to talk about the force acting on a piece of material consisting of many atoms, and go to a continuum limit, then that would be on the form times, this would be replaced by, charge density, rho E, and this would be QE. Q of E will be replaced by the current density. And now, if you compare the two expressions, you can identify this term is part of the current. And it is related to polarization, so that from this term, I found out that there is a contribution to the bound touch current coming from this term. It's del P by del T. Plus other terms that appear that's from whatever we have not considered. But you know the result because those terms not considered explicitly, in fact, are given by the static case. So this is, for the static case, you remember this term is curve of magnetization. Whereas for the bound touch density, there's no new contribution. Nothing involving del by del t, but the usual, the static result, which is minus divergence of P. All right. With that, let me. So all the tedious calculations will just give us these two expressions for the bound currents and bound charges. And then all the new result is, in fact, this term. All right. So, here. So let's go back, okay, to the Maxwell's equations. Forget about the and let's drop subscripts. So rho here, of course, consists of the sum of the bound toxicity as well as the free part. By free part, we mean the toxicity, not the given at polarizations, metalizations, etc. And that we have the current density is equal to the sum of the free part and the bound part. So this is the bound frequency is minus divergence of polarization. And thus current density is given by the sum of the free part. And now the bound part, there are two terms plus del P by del T plus curl of M. So let's substitute this. Go on the right side of Gauss law. And this S, rho sub S. Well, to start with, in fact, it might be a good idea to put epsilon naught to the other side and then do that. So rho sub S minus divergence of P. And okay, so this equation J is given on this one. So this will be replaced by T sub F. And okay, for this, let's in fact divide up by mu naught from both sides. So J is df plus this piece. So I have plus del P by del T plus curl of M. So this is now the Ampere-Maxwell's equation along, and this is now the Gauss law for the Maxwell's equations inside the method. And I can okay, so what should oh, okay, I can use this one. All right. So let me take a look at the first equation. This equation. Okay. Since this term involves divergence and this term involves divergence, it's natural to combine them together. So let me move this to the other side. And I will have, divergence of epsilon naught E plus polarization. That would be the free charge density. And as you recall, you encountered this combination before. This sum is denoted by D. Vector. So that I can rewrite the first Maxwell's equation as divergence of E is rho F. So this is this electric displacement defined to be the sum of these two terms. Electric displacement vector. All right. The other two equations remain, this and that. But let me take a look at the last one, the complicated one. The last one, the complicated one, would be of this form. So that I have the curl of B divided by mu naught, not curl. But this curvature motion, let's put it to the outside. So minus m. And that would be, okay, the free charge density, then plus this combination of del by del T of epsilon naught E plus P. But epsilon naught E plus P is nothing but a displacement vector P. And as you may also recall, you encountered this combination of B and M before. This is denoted by the H vector. So that the last Maxwell's equation can be rewritten as the curl of H is equal to the free current density plus del E by del T. All right? And let me copy down the other two Maxwell's equations. And this one involves curl of E is equal to minus del E by del T. And then this equation. And then this is space. It is this divergence of P in 0. These four equations are Maxwell's equations inside matter. Maxwell's equations inside matter can be written in this form. In terms of the sources, the free touch density, free current. And you remember also D is given here. And H, oh, what happened? How come? I think this thing erases. E minus A is H. All right? And also, let me also mention that if that piece of material is a linear medium, so for a linear medium, then of course we know that the polarization P is proportional to E. Remember, epsilon naught times the electric susceptibility, cos E times E. And that for the linear magnetic medium, remember H is related to, M. Is related to the magnetic susceptibility, something H. And in that case, then so that D is equal to epsilon naught E plus P, which is this one. So epsilon naught is outside E. I'm sorry. E is outside 1 times E. This term. And P is not this one. So it's epsilon naught times K is plus K. And that H will be equal to, where's H? Here. 1 over mu naught E. Okay. M can be moved to the other side. Okay. Plus M. So that H is equal to mu naught B over mu naught. Okay. Minus M goes to the other side. Minus M. And minus M is this. So that the minus becomes plus to the side. So it's 1 plus chi M times H. So that H can be rewritten as 1 over mu naught 1 plus diminished substitutability B. And of course, we call this to be the permittivity of the material, of the medium. And we call this to be, what's in the denominator, we call it, we denote by mu, which is the permeability of the medium. So that, D is equal to epsilon E, medium, and H is equal to 1 over mu. All right, one more thing, then we'll stop. Okay, and since everything's here, and I can erase this now. We're done. Okay, we should now talk about boundary conditions. Okay, for this set of Maxwell's equations. So then let's say that we have two different media, one on top of the other one. So medium 1 and medium 2. Separated by surface. Locally, of course, the surface is flat. And we would like to find out the boundary conditions across this surface. The boundary conditions. Well, by now, I hope you're familiar with the derivation of boundary conditions. Once you have, the Maxwell's equations or the static case, you learned from the study of mental statics and electrostatics how to derive those boundary conditions. For example, there are 4 equations, 2 involve divergence, 2 involve curl. And for the 2 equations involving divergence, all you have to do is, in fact, consider the volume integral of both sides, use Gauss theorem converted into surface integral, and you apply that to a pill box with half of the pill box in medium 1 and the other half in medium 2. And with the size of the pill box eventually shrink to 0. So that what picked up would be the volume inside this pill box. So that from this one, and then the pill box, of course, the area integral of over top half, of course, will give me the area times area cancel out. So just the displacement vector, the perpendicular component above, relative to the one below. That's a minus sign because in the pure box, for the upper half, the vector, the unit vector points up, whereas for the second half points down. So that's a relative minus sign. Below is equal to, you have here, now what's the charge inclusion inside that? Of course, it's nothing but, sigma F. And this one, of course, is simple. If you get E perpendicular above, relative to E perpendicular below, is 0. For the curve, all you have to do is to consider the area integral of both sides around for an imperial loop. So in the imperial loop, one half of it is above the surface, the other half below, with the sides shrinking to 0 eventually. So that you can convert the area integral of the curve to be the line integral for this, along this line and along the other side. The side will shrink to 0, so there will be no contribution coming from the sides. And for the right side, so I'm interested in the area integral of B. Since the area eventually shrinks to 0, so the right side will be 0. So that this will give rise to E parallel to the surface above, relative to the E, see, on this side upper, the contour integration goes this way on top, and the other side way on the bottom. So minus E parallel below. That's 0. And finally, this complication, there will be no, do the same thing, as for this case, then we take this equation, take the area equation, construct an imperial loop, take the area equation. Again, there will be no contribution come from this since the area will shrink to 0. So this one will give me, it's more complicated, it's not as simple. And you have to take a look at how things are done for the static case. And you'll find out that H parallel above, relative to H parallel below, that's equal to, in fact, the free surface current density cross N being the normal to the surface. Okay? And let's see. One more thing, then I'll let you go. Of course, for a linear medium, we can replace this by permittivity of the medium, perpendicular above, etc. Similar for this one. And for this, you can replace it by, B divided by the probability of the median above relative to one below. So with this, I conclude this lecture.